Right, g'day guys, welcome to lecture 7, types of force. Here are your learning intentions and success criteria. Please complete the KS table. Pause the video while you complete this. Alright, so having a read through here, I want you to understand different types of forces and be able to identify them in scenarios. Here we've got to identify our forces acting on an object, so we need to know those forces. I need you to be able to recall the acceleration of gravity near Earth is a constant of 9.81 meters per second squared, and you will need to get down to 9.81. You cannot just use 9.8. And finally, constructing a free body diagram. So we're going to expand on this one. We saw this one last lecture, but we're going to continue with that. Can you construct a free body diagram? But I've added a little bit more using these forces that we've talked about. Okay, now the text through chapters 11.1, 11.3 and 11.4 mention some stuff about forces. So first let's talk about those. Now forces are generally split into two groups, contact and non-contact forces. Now the non-contact forces are the big ones of the universe. So we're talking about gravity, the strong electromagnetism, the strong nuclear and the weak nuclear force. And when we talk about gravity, we're going to be talking about this force called weight. And we'll talk about that a little bit longer, so you haven't covered that yet. The first two we're fairly familiar. Gravity pulls us down, pulls things together, while electromagnetism, if you've ever played with magnets, and I hope you have by now, we know that they push and they pull. Okay, so gravity is only a pulling force, and electromagnetism can be a push or a pull. Okay. Now mathematically it doesn't matter if it's a push or a pull, you just have to keep in mind direction about, is it pushing something away or is it pulling me towards it? Now contact forces happen when things interact with each other. These ones here don't need to interact, or at least they don't need to, they don't need to touch. That's why we call it non-contact. Right now where you're sitting, there is some amount of gravity from every person, every object near you, even if you're not touching it. You might be sitting on your bed, right? Which means that the rest of the house is actually slightly pulling your body because of its mass and your mass. All objects with mass have a gravitational pull towards each other. Okay, electromagnetism. This just deals with magnets mostly. Electricity has a little bit of it. We'll talk about that's why the word electro is there at the start. We'll talk about that a little bit when we get to that unit. We won't see strong nuclear or weak nuclear forces at this level. We will see it a little bit later this year though. All you really need to know is that it's a push or a pull. Now, contact forces, though, these are when things are touching, and the text has covered a few. It's covered tension, it's covered the applied force when someone actually does something, and it's talked about the normal force. And we're going to look at friction today as well. Now, a tension happens when you have a being pulled or hanging from a rope. Okay, there has to be something like a rope or a string or something to that effect attached to an object, and then the rope is transmitting the force. A swing, for example, is a great example of tension, that there is something connecting or pulling on the seat at the bottom of the chain that connects it to the bar at the top. Applied force is anything that's just being pushed or pulled. And the normal force is what happens when one object is pushed into another but stays still. So for example, you right now sitting on your chair or sitting on your couch or sitting on your bed, your bottom is pushing down onto the surface underneath you, but you're not going through it, so something has to be pushing back. We call this the normal force. Okay? Let's have some examples of these for a second. So if I say I have an object, it is a block on a surface, and I have a rope, and I have a pull force here on the rope. Well, that rope here, if I'm pulling from this end, transmits down here to the block, and so there is a force due to tension. We give it a capital T for tension. There is a common shorthand for it, pulling on this object. Okay, and when we think about tension forces, all we really care about at this point is that it just transmits the force. There's some interesting stuff with pulleys. It's not part of our syllabus, so don't worry about it. You will see that if you do any of your own reading, more than likely. The other one I was talking about is applied forces, and so let's go back to our object. Perhaps it's a big object like a car. I know my cars look very much like blocks, and so this person here might be pushing on it, and so we would say a force applied, or I tend to use P for push. It doesn't really matter which one you use, you just got to emphasize that this is the push force that's happening onto it. If we were to do it without our person, we would just draw it like this. Force applied equals, like 5 newtons or something like that. Now, the last one is the normal force, and the normal force is always perpendicular to the surface it rests on. So let's go back to our block. If this thing is getting pulled down by the force of gravity, and there is a force of gravity acting back up the other direction, at the surface between here there is a normal force from say our surface onto my block, and there will be a normal force from my block onto my surface, which is why these things don't go into each other. I've drawn my arrows very, very poorly to scale here. These things should all be about the same size. They always happen perpendicular to the surface. That means 90 degrees to the surface. If something is on a ramp, gravity would act this way, but the normal force would act this way. Now, we will deal with ramps probably around early term 2, so it is not part of what we're dealing with now, but it is something for us to keep in mind. Okay, so the normal force is always perpendicular, and normally this is equal to the weight of the object. But if we have, say, 2 objects, one on top of each other, the normal force here, so this normal force, is going to be equal to the sum of the total masses, not just the one mass. It's going to be equal to the total mass pushing down onto it. If I then go and push down on top of it, I can't draw a hand, let's draw a person. If I go and push down on top of it, even though I am not adding more mass to it, I am adding more force, and so the normal force has to increase. Otherwise, the object would have to move, because if it's still and me pushing on it doesn't make it move, well, Newton's first law says that the forces must be balanced, and so that normal force must increase. Now, the next one is a really important word. That's why I've given it their own slide, and there's a whole chapter on this. Weight is a really important word in physics. If you go and ask someone what they weigh, and you don't get slapped for it, they're going to tell you, oh, I weigh 50 kilograms, or oh, I weigh 95 kilograms. In physics, that is wrong. You do not weigh 50 kilograms. Your mass is 50 kilograms. When we ask what something weighs, we are asking how much force is being felt due to gravity. When we ask mass, we are asking how hard it is to change its motion. Commonly the word mass is called inertial mass. More mass equals harder to change its motion. Weight is a force. Okay, so if we want to work out your weight, we know the formula, A equals F over m. Okay? And so the force of weight will equal acceleration times mass. Now, if me rearranging this to find this, it was very, very confusing. You need to really double down on your algebra to come see me. Now, the m is the mass of whatever object we're talking about, but the a is important. The a in this case is gravitational acceleration. Okay? Now, on Earth, the acceleration due to gravity is equal to 9.81 meters per second. Now, it does vary slightly over the planet, but this is the standard. Sometimes this will be written as just g equals 9.81 meters per second squared. And that's, I believe, how it's written in your formula booklet, so be aware of that. I would recommend that you memorize it because it will speed up your problem solving. If you have to flip through the booklet to find the acceleration due to gravity and you're going to use it a lot, you will probably waste a lot of time. Now, Note, I have used lowercase g here for this, not capital G. That's a different thing to do with gravity called the gravitational constant, so you have to be careful with that. I personally prefer to use AG as my symbol. If you use that as well, they will be able to understand that in your exam. Now, this means that your mass, so the force of weight, will equal the acceleration due to gravity times mass. So work out your actual weight. If you want to annoy your mother, work out her actual weight and tell her she weighs something like 700 newtons, and she will probably lose her head at you. Mass, same everywhere in the universe. Weight depends on gravity and is a force. You go to the moon, you're not going to weigh very much, because the gravity, the gravitational attraction, the acceleration due to gravity is very little. Go to Jupiter, you're going to weigh a lot more than what you do now, because Jupiter has a higher gravitational acceleration, okay, because it's got more mass. Now, friction is the last force. Now, friction comes in three flavors, or three different types: static, kinetic, and rolling. Whenever something is moving, you must consider friction, unless the question specifically says to ignore it. We're going to look at projectile motion later on this term, things flying through the air. We ignore friction. If we're talking about something moving across a surface, like something sliding along, unless it specifically says to use friction, or you're able to use friction, perhaps they don't give you enough information, you have to consider it, otherwise you just ignore it. Now, the important thing to remember about friction is friction always acts against the direction of motion. If something is moving to the right, the friction will act left. If something is falling down, the friction force acts up. If something slides up a ramp, the friction force acts down the ramp until the surface slides down the ramp, and then the friction changes the other way. So let's draw those three. So if I have something going this way, my friction force goes that way. If I have something falling down, the friction force goes that way, and we call this friction drag. We'll talk about that a little bit later. If I have something going up a ramp, the friction force acts this way. Oops, that was a horrible lowercase f. Until it starts to slide back down, and then the friction changes to the other direction. If I have something that is being pushed applied force, then the friction force will be there. Now note, friction force is not a force pair. Okay, the pair, or at least a pair with of applied force. The friction of this pairs with the friction of the ground or the surface on the box pairs with the friction of the box on the surface. Okay, friction pairs with friction. If I'm pushing against here, this box pushes back against me. If you don't believe me, put your hands against the wall and give it a shove. You'll feel the force push back into your hands at the same time. Now, if that friction balances the applied force, then there will be no change in velocity. So if this friction force here is equal to this, there will be no change to this velocity. Okay? Let's say that the velocity was equal to 1. If these two balance, that velocity won't change. It will always be 1. And remember Newton's first law. It might stay still if it was already still, or it will stay moving at constant speed. Okay? It doesn't mean if there's friction that's equal to the applied force that it doesn't move. It means that the movement doesn't change. You've got to keep that in mind. If the applied forces are different than the friction force, then there'll be acceleration. It might speed up, it might slow down, depends on which is larger. Now, of these three, static friction is always the largest. Okay? And that's what happens when you push or pull on something that is stationary. That's why it's called static friction. Static means not moving. If your push or your pull is larger than the static friction, it starts to move. Now, kinetic is always less than static. Okay? And there's a lovely graph I have here. Let's see if we can get this up over the top. Let's go back a bit, get rid of this for a second. should put this on a separate page. So here we have a graph that is showing the friction force over here against time. And what's happening here is, imagine that you're pushing slowly against something and pushing harder and harder and harder. And what we see here, as we push harder and harder and harder, the force gets bigger and bigger and bigger. It goes up roughly at a steady straight line. Okay, obviously it's very hard to slowly increase your force steadily, but we see that as we push harder and harder, this, in this case pull, this increases as well until it gets to a point, and then suddenly it drops. Here they've called it the breakaway force. You don't need to worry about terminology like that. And we see that the force changes. It goes down much, much, much more. And it's roughly constant. It vibrates a little bit. Have a look at the text to understand a bit about what's happening there in terms of the actual the physical properties that's causing this. So kinetic friction is always going to be less than static friction. Now, you don't need to calculate static or kinetic frictions. You certainly can, and that might be something that you want to do for an extension project when you do your experiment. However, it's not part of the syllabus, so that makes it good as an opportunity for you to do further learning. The last one is rolling friction, and rolling friction is always very, very small, even compared to kinetic friction, because the surfaces don't slide over one another. They just push down, and then the next bit pushes down, and so it rolls over. So there's no real movement of the surfaces relevant to each other. They don't slide past. Now, Chapter 11.7 in the text also talks about a special type of friction called drag. Now, this is not part of the syllabus, but Dr. Walding does happen to quite like it. And you might want to read over it as a possible adjustment for your student experiment in Term 2. Don't do it right now, but keep it in mind for down the track, because we're going to do some stuff with objects flying through the air, but we're not going to consider drag. We're going to pretend that it is a frictionless environment. The real world has friction in it. So you might want to look over that, because it might help with developing a proper adjustment for your experiment. Okay, but we'll talk more about that when we get to it. So in this video we've got to cover the following. We've covered the 5 types of common forces: tension, applied force, normal force, weight, and friction. We've explained mass versus weight. Really important to get that language right, because that's the sort of stuff that would appear on that final exam at the end. And if you're talking about masses of stuff in your experiments and you write weight instead, that would cost you marks of communication. And we've learned about different types of friction and how it slows down motion. For your entrance to class, please complete Check Your Learning 11.5, questions 1 to 4, and 11.6, questions 1 to 4, and submit them on the 1.7 space on eLearn. Thanks very much for listening, guys. Have a good evening.